Okay, so last time we barely stopped here, and actually we know that the okay, so this is absolute value of psi x squared, which means this is the probability density function of x, and this is actually the probability density function in the k domain. So we know sigma x is actually this term. This is sigma x, which is 1 over square root of 2 times sigma k, and yeah, this is some sort of sigma k, but if we use sigma k, this is also sigma k, so maybe I write it as a delta k. So this is delta k, and actually this one is so-called the delta k. It's the delta k, so this is nothing but a sigma k over square root of 2. And if you still remember, we have a identity like P equals h bar k. P equals h bar k. P is the momentum of the particle. K is the wave number. So if k has a derivative here, which means if we take the derivative on both sides, we have something like dp equals h bar dk, or we can actually write it as sigma p equals h bar. Actually, it's not sigma k, maybe we can write it as delta k, which is this one. So finally, we have sigma x, sigma p equals, sigma x is actually this one. So it is a 1 over square root of 2 sigma k. And sigma p is this one. So we have h bar times delta k, which is this one, sigma k over square root of 2. So finally, we have sigma k and sigma k cancel each other. We have square root of 2, square root of 2. So finally, we have h bar over 2. So actually, this is the equality condition for the Heisenberg uncertainty principle. And actually, that sigma x times sigma p must be larger than or equal to h bar over 2. Okay, so now let's take a look at a sample problem. Okay, so here it says, assume that an electron is moving along an x-axis, and that you measure its speed to be 2.05 times 10 to the 6 meter per second, which can be known as a precision of 0.5%. So what is the minimum uncertainty as allowed by the uncertainty principle in quantum theory, with which you can simultaneously measure the position of the electron along x-axis? Okay, so actually we have px to be m times vx, because here it tells you that the speed in x-axis is this one, and actually is an electron, so the m of it is 9.11 times 10 to minus 31 kilogram, times Vx is 2.05 times 10 to the 6th power. Okay, so this value is 1.87 times 10 to minus 24 kgm per s. So this is the momentum. And it tells you that why okay, Okay, so it tells you that the precision of it is 0.5%, which means that delta px, delta px is 0.005. This is 0.5% px. So this is 0.005 times this value, 1.87 times 87 times 10 to minus 24. So this value is 9.35 times 10 to minus 27 meter per second. Okay, so actually I still using the delta x delta p larger than or equal to h bar, but yeah, it doesn't really matter. So we have delta x equals h bar over delta p x, something like this. So h bar is 6.63 times 10 to minus 34 over 9.35 times 10 to minus 27. So this is 11 nanometer. Okay, so next we talk about something interesting. So this is something like refraction from a potential step. So it says here, we send a beam of great many non-relativistic electrons. Non-relativistic means you don't care about the relativistic effect. You just assume the velocity is low. Actually, you can still consider the relativistic effect here, but it will make things more complicated. So here, for simplicity, just assume that we assume the electron is low enough, so we just ignore the relativistic effect. So each of the total energy E along an x-axis through a narrow tube. So this is a narrow tube like something like a wire. And then initially they are in region 1, which the potential is U equals 0. So there's a potential energy or electric potential, something like the voltage. Actually if you still remember in chapter 24, we have a U equals QV. And now we have electrons, so Q is nothing but minus E, minus 1.6 times 10 to minus 19 Coulomb. Okay, so here, but at x equals 0, they encounter a region with a negative electric potential, VB. So you can imagine here, we have two segments of wire. This one, we have a voltage, V0 here. And then this segment, which does not touch this one. The voltage here, VB, is smaller than 0. Just a fixed value, less than 0. In such a way, there is a potential. The potential will be larger than 0, because if this V is negative, this Q is negative, E is also negative. So negative times negative is positive. So finally, we have a positive energy step here, positive energy step here. Okay. So, but they encounter a region with a negative electric potential VB. The transition is called a potential step because this is called the potential energy. So here there is no reference, in reference there is no potential energy here, but here there is some potential energy. So it's just like a potential step or potential energy step. The step is said to have the height UB. UB is nothing but negative E times this VB, times this VB. Okay, so which is the potential energy an electron will have once it passes through the boundary at x equals 0, like this. So this is the basic setting. So this is something which is not agree with the classical mechanics. Okay, so so for classical mechanics, suppose you walk upstairs. So there may be a staircase. Suppose you don't take the elevator, and then you need to walk up from the front door to first floor. Then you need to walk upstairs. As long as your foot is higher than the step, then you will not block by the stair. If your foot is not high enough, then you may kick somewhere here. Then you may fall down. But if your foot is high enough to overcome this so-called potential, this is actually the gravitational potential, not the electric potential, but the idea are similar. So as your foot is high enough to overcome the MGH, the gravitational potential, then you can walk upstairs. But here some interesting fact appear here is that suppose we have an electron here. We have the potential step here. If the energy, in this case, all the energy on the electron is the kinetic energy. If we consider in a non-relativistic electron, so the kinetic energy is 1/2 mv squared. So this energy E is nothing but K equals 1/2 mv squared. You need to care about the notation. In this chapter, we use E for the electron, which does not count the rest energy. But in chapter 37, when we use this E, in chapter 37, this E counts the rest energy plus the kinetic energy. In that chapter, E is gamma mc squared. E0 is the rest energy, which is mc squared. K is the kinetic energy, relativistic kinetic energy, which is gamma minus 1 times mc squared. But here, we still use the notation E here, but it only counts for the kinetic energy. Or sometimes it counts for the sum of the kinetic energy and the potential energy, but not count for the rest energy, the energy related to the mass of the particle. Okay, so here if we assume the kinetic energy is higher than this potential, of course in classical mechanics, this particle should be able to go through this potential step. But in quantum theory, it's not the case. It may be refracted by this step. Even this step is lower than its energy, then this particle may have some probability to be refracted by this potential step. Let's see why it will be like this. And of course, we need to solve the Schrodinger's equation. And if you still remember, this is the Schrodinger's equation. So we need to solve this. Originally it should be a PDE, but if we just isolate the time factor, their exponential j omega t, then which is this phi is only related to x if we consider in one dimension. Okay, so actually we need to solve this one variable PDE, but it is actually a so-called PDE with boundary condition. Boundary condition 有边界条件的偏微分方程PD with boundary conditions. Okay, so this is so-called the boundary condition. On the left side, maybe we can call it region 1. This is region 1. Sorry. On the left side, this is region 1. On this side, the potential energy is 0. So U of x is 0 when x is smaller than 0. This is x to be 0. And then this is the x-axis. So on the right side, x is larger than 0. On the left side, x is smaller than 0. So as the Schrodinger's equation include the potential, so we need to separate in two regions. This is region 1. For region 1, u equals 0. U equals 0 here. And for region 2, we have u equals ub, and actually this ub is negative e times vb, but yeah, maybe we just skip the vb there. You only need to know, we set up this setting like this. We have two segments of tube, and then this voltage is V equals 0. This is a VB smaller than 0. Okay. So we can be able to solve the Schrodinger's equation for these two region. Okay, when u equals 0, so it is simplified like d2 phi dx2 plus 2me over h bar square and then phi, because u is 0, so we only have 2me, e minus 0, so this is e, 2me over h bar square and then times phi equals 0. So you should be able to solve this second order constant coefficient ODE. Yeah. So here we just define k to be square root of 2me over h bar. So this becomes d2 phi dx2 plus k square phi equals 0. And then when you solve this one, you can write s squared plus k squared equals 0. So s equals plus or minus jk. And in that case, or ik, so we have a times exponential to ikx plus b times exponential to negative ikx here. So this is the solution. This is the solution to the Schrodinger's equation in region 1. And of course, a and b are unknown coefficient. We need to determine. And we'll determine it a bit later. After we find the solution in region 2, then we will be able to find what is a and b here. Okay, so the next one is x is larger than 0 in region 2. We have u equals ub. ub is larger than 0, but we at least know that E is larger than ub. The kinetic energy of the particle is larger than the potential step. So we know that. So this term is nothing but E times ub. And E is larger than ub. So E minus ub is still a positive value. It's still a positive value. So now we assume that, so that equation becomes d2x, d2 phi dx2 plus 2m e minus ub all over h bar square phi equals 0. So this one and this one are only different by this. This is E minus UB. So here we define K sub B equals to square root of 2m multiplied by E minus UB, and then all over H bar. So now it becomes d2 phi dx2 plus kb square x phi equals 0, like this. So the solution should look so similar that it should be something like c times e exponential to I kbx plus d times exponential to negative I kbx. And we know that this is positive. This positive means the wave is propagating in positive x direction. This one means the particle propagate in negative x direction. So for region 1, this particle might be reflected by this potential step. So we include both terms here. But for region 2, actually the particle is coming from the left side to the right side. So as long as it passes through this step, it should go to the right side. It cannot go to the left side. So we just ignore this term here because we will assume that the particle is going to the right side. So we only take the first term for this solution. Okay, so we only have this term c times exponential to I kbx. And now we already find the solution. So this is the solution for region 1. This is the solution for region 2. And if you still remember, I talked about the boundary condition. The boundary condition means at the boundary, which means x equals 0. In this case, maybe for some other case there may be more than one boundary, but in this case we only have one boundary. This is the boundary between region 1 and region 2, which is at x equals to 0. Okay, so the boundary condition here includes this one. The boundary condition. This is the first boundary condition, is that the phi is continuous. The wave function should be continuous at the boundary, which means that when we plug in x to be 0 at the boundary, x to be 0, then the wave function in region 1 and in region 2 at the boundary on the left side and on the right side should be the same. So if we plug in 0 here, exponential to 0 is 1. So we have a plus b on the left side. And then phi 2, when we plug in x to be 0, this is 1. So we have c on the right side. So we have a plus b equals z. So this is the first boundary condition. And of course we still need another one. And so keep in mind that we have this is the solution in region 1, this is the solution in region 2. And then the second boundary condition, the first boundary condition is phi is continuous. And the second boundary condition is that the phi pi is also continuous. The original function of the wave function is continuous, and also the first derivative of the wave function is also continuous. So if we take the derivative of phi 1 x prime, so we have a times ik exponential to ikx plus should be negative. Negative b times ik, because this is negative ikx, so when we have the chain rule, it is negative ik times this one. So we have negative b times ik exponential to negative ikx. And then if we plug in 0 there, because this 0 is the boundary, if we plug in 0 there, this is 1, this is 1. So we have actually aik minus bik, or iak minus ibk equals, and then also we take the derivative for phi 2. So phi 2 x prime is c ikb exponential to ikbx. Okay, so if we take x to be 0, so this one is 1, we have ickb. So I can be cancelled. We only have ak minus bk equals c times kb. So we have these two conditions. Actually, we have 3 unknown variables, but yeah, actually, for the boundary condition, we only write out 2 equations here for this case. And of course, if you still remember the probability density function should be integrated to be 1 from negative infinity to infinity. So this may further give you the 3rd condition, but yeah, here we can just skip that one because it makes things complicated. What we here need to find is we want to find the refraction coefficient and the transmission coefficient, which means that how many percentage the particle can go through this step, and how many percentage the particle will be refracted by the potential step. This is the transmission coefficient and the refraction coefficient. And wow. And actually, actually you can simply solve these two. Actually, if I remember correctly, maybe the slides I upload to the Moodle has a typo mistake. This one should be 4 rather than 2 there. If you check the slide on the Moodle, I forgot to update that one. So actually, you can simply solve these two. You will be able to find that. If you can have something like a plus b equals c, and then a minus b equals c times kb over k, like this. And then if you just add them together and then divide by 2, b plus b and negative b will be cancelled, and then on the left side we'll have a, and then 1/2 of c times 1 plus kb plus k, or you can write it as c times k plus kb over 2k, something like that. Yeah, like that. And then if you just subtract them and then divide by 2, you will get b, because subtract them, a and a will cancel. And then you will get 1/2 of a k, and then this one minus this one should be c times k minus kb. You get these two solution, a and b in terms of c, and of course in terms of k and kb. Okay. So the refraction coefficient is something like b squared over a squared, because if you consider here, we have something. A is propagating to the right side. We have A exponential to ikx propagating to the right side. And also we have B exponential to negative ikx propagating to the left side. And then here we have C exponential ikbx propagating. Just go through the potential step. So when you need to consider the refraction coefficient, which is like the probability of this wave divided by the probability of this wave going to the right side. So this is the refraction coefficient. So we have B over A and then absolute value and then square. So if you just divide this one by this one, CC2K will be cancelled. We will have K minus KB over K plus KB quantity squared. So this is the refraction coefficient. And then we will have transmission coefficient because the particle is either go through or reflect. So 1 minus this refractive coefficient is the transmission coefficient. So 1 minus this one is a 4kb over K plus KB quantity squared. So this is the transmission coefficient. Okay. So let's take a